So this is the pipeline that starts from the data. The data is in the format that your algorithm can process. You know, the input part, output part, basically a list of IO, right? Yeah, and then you can run experiment. You can measure the performance with the classification again. Decent matrix plot. If it's binary, then I would insist that you also show the receiver operating characteristic curve. Okay, so, oops. So, new share. Where are we? Yeah, so this is the problem that I guess it hung a little bit, but okay. So we try a few things. For example, if this is a neural network, then this is the confusion matrix. This is the ROC. The area under the curve is 0.91, so it's very, very good. Again, this is not a difficult problem. Let's see, decision tree. Okay. It's even better. Oh, okay. Sorry. It's with respect to the testing and training. So it's a different data set. Okay. Supporting vector machine. So you can try a few things. Now this sample is a little bit funny in that a lot of time the testing performance is better than the training performance, but most of the time you don't get that. See, like this one, you get perfect prediction. Yeah, it just happens that you have a very few. So in this case, you see, this is a neural network. The training performance is near perfect, but it's not perfect. But it turns out that the testing performance is perfect. So this is rarely the case. You rarely get the case like most of the time the training performance is better than the testing performance. Yeah. So that's an example of how I would do it. Again, professionally, I tend to do two things. I get to do complete experimentation, try all the methods, all the deep learning algorithms, and I also try to let the Mathematica give you heuristically what you think is the best automatic choice of algorithm. Okay. Now, so let's go to the final slide today. Okay. Which is this. Now let's do the building. Okay. So this is the pipeline, and this part here, building the machine learning engine. If it's a neural engine, okay, if it's a neural engine, you have several options. Yeah? Somebody was asking me before the beginning of the class, asked me at the beginning of the class, can we use a pre-trained model? Yeah, it's very valid. Yeah, this is how it works. So, when you specify a neural network model, so what's fixed? The input and output, right? For example, an input for, say, image recognition, right, could be an array data, 28 by 28, right? If it's color, maybe it's 28 by 28 by 3, right? So the dimension of the input is determined by your I/O, right? By your variable space. But what goes on here, from here to here, is the neural network. Okay? Now, I showed you earlier what happened when we rely on Mathematica to just give us a neural network. Just say the method is neural network, build me a neural network. And that tends to work for a simple problem. That's not very difficult, that's not complicated. For a really difficult problem, chances are you have to be more technical in terms of specifying the neural network architecture. You have to do research, that this kind of architecture works well, that's the experimentation, right? So, It's a two-step thing. First, you have to specify the architecture. In other words, a neural network is like a building. You have layers of neurons, and you have another layer, and another layer. So you can think of a building as many stories. Okay? A 3-layer neuron is like a 3-story building. Okay? 50-layer neurons are 50-story building. But each layer can be different and have different types of neurons. And have, logistic regression, we'll learn some other thing. But basically, you have to specify the number of layers, the number of neurons per layers, and the type of neuron in that layer. Yeah. So, I'm going to say repeat after me, right? Once you have the input and the output phase, you have to determine how many layers in between, how many neurons at each level, and how many types of neurons. Yeah. Now, we only learned the logistic type, but maybe there are other types. Yeah, and we'll talk about another type later. Most of the time, the same layer will have neurons of the same type. Yeah, again, this is as convenient. This is general enough, powerful enough. You don't have to fiddle with different types of neurons at the same layer. Yeah. So, how many kind of neurons do you know? How many types of neurons do you know? How many types of neurons do you know? Well, a neuron is called, it works the same way, right? It works the same way. Activation. Yeah? So far, I only talked about this one, this guy here, logistic regression looking. Remember that? Okay. You see the third line, logistic regression, that function. It's the same function using logistic regression. And if I use that to represent my neuron, then I can say a logistic regression is equivalent to one neuron. Right? But it's equivalent to that kind of neuron. There are other kinds of neurons. There is this kind of neuron called hyperbolic tangent neuron. There's this kind of neuron called linear neuron. There's this kind of neuron called rectifier. Linear, prelude. You can think of it as different ways that the neuron activates. It activates, in this case, if there's no signal, if the signal is weak, it doesn't output anything. If the signal is strong, it outputs 1. Now, if it's a hyperbolic tangent neuron, if the signal is weak, it actually sends a signal -1. If the signal is strong, it sends a +1. Okay? And there's a smooth curve in between. A piecewise linear is like a logistic, except instead of being a smooth transfer function, it is piecewise linear. There's a sharp edge there. Okay? Now, of all of these, I can tell you this: the most realistic, I think, in my opinion, model of a biological neuron is either going to be this one or this one. Why? Because in biology, you don't have sharp edges, right? It's kind of an analog process. So a biological neuron will work like this or like this, most likely like this. Okay? So if the signal is weak, it doesn't send anything. And eventually it sends a signal of 1. Okay? That's what the biological neuron would look most realistic. Now, technically, you can run into troubles, and this is something you don't know. I don't expect you to understand, but this just hear me out. Okay? When you have many layers of neurons, it's like a very tall building called deep architecture. Very deep, very tall, very tall, very deep. Okay? In a deep learning architecture, what happened is, because this thing is flat, the algorithm kind of gets stuck. This is very technical, you don't have to understand it. This is practical. Yeah? The algorithm kind of gets stuck. So it turns out that whereas in the 1980s, the multi-layer perceptron maybe has 10 layers at most. Okay? And they were using this. They were using this successfully. When you need to do deep layers, like 20, 50 layers, it turns out that that kind of neuron fails. It kind of gets stuck algorithmically. So the one that they tend to use nowadays turns out to be this one, which is called rectifier. Basically, the signal is weak, it doesn't fire. It is strong, it sends the signal. Now, is this one realistic? Is this a good model of biological brain? No, it's not. That brain is not the right way to model human neuron. Human neuron doesn't work like that. So it's not realistic. But in terms of the algorithm, it works well. Okay? So this is something that, again, machine learning here departs from artificial intelligence aspiration. Okay? Now, so let's say these are the type of neurons. These are the type of neurons. Yeah, these are the type of neurons. So we have, let's say, 5 types. Yeah. So when I say specifying neural network architecture, what do I mean? How many layers there are, how many neurons in each layer, and what type of neurons. Yeah. Generally, as a rule or as a matter of practicality, all neurons from the same layer are of the same type. So if we have radius, it's all radius. We have logistics, it's all logistics. We have hyperbolic tangents, it's all hyperbolic tangents. We don't have hyperbolic tangents next to radius, next to, we don't do that. Yeah? For all practical purpose, we never do that. And that's complex enough. Life is difficult enough. Okay, so that's what we mean by specifying the architecture. Okay? So the first thing, you specify the architecture. Once you specify the architecture, then you hook it up to the data, right? And then you specify the learning algorithm. Remember that I told you the little step you take, right? Well, there are many ways of taking little steps. Right? So you can say, I want to go downhill. Right? I look locally at the direction of greatest descent. Okay, and I go down. And I keep doing that. Take one step. That's one algorithm. Another algorithm would be something like this. Wherever I start, I take big step. Look at the gradient. Then I take a smaller step. So I take successively smaller steps. That's another algorithm. Another algorithm would be something like, I go downhill, but occasionally, out of boredom, I go uphill. Okay? Why would we do that? Because sometimes you want to escape the local optimum, right? Or sometimes you go downhill with respect to the data set. And then you split it up to another part of the data set. And you go downhill on that. So it becomes random as to the direction of downhill. Okay? That's called stochastic gradient descent. So you have to specify the architecture, the learning algorithm, right? And then you train the model. Now, for the purpose of this class, I'm going to completely ignore the learning algorithm. Okay? And this is where you can rely on automatic default. Okay? Chances are, if you work with scikit-learn, the automatic or default would either be this thing called SDT, so stochastic gradient descent, or this thing called adder. It's very popular. likewise, in Mathematica, you can also specify the algorithm, or you can leave it as default. In this case, I'm going to leave that as default. Yeah. So you have to specify the architecture, the algorithm. Now, I'm going to ignore this part. Yeah, because this is very technical. It's only the people who are researching into neural network software who say, oh, this algorithm works best under this condition, this algorithm works best under a certain condition. Okay, but chances are you don't have to worry about that. It's going to be something either SDB or Adam. Yeah, these are the two flavors. Yeah. Now, likewise with architecture. Okay. ReLU is going to be very popular nowadays. So again, these are all the nitty-gritty configuration. It's like if you want to build a building, maybe you just say, I want a 5-story building, right? But if you know what you're doing, you can put the architecture. Okay, I want to have this many rooms on the first floor, this many rooms on the second floor, and this type of roof. Right, so it's that kind of thing. It's that kind of sense that if you know what you're doing and you're willing to do the experimentation, build different kind of architecture and try it. If not, you just let the algorithm use some kind of default heuristic. Yeah. So that's what I mean. Now, let's go back to our slides. So again, you specify the architecture, and then you create. And here's where it becomes very important for your project, especially the Wang team. Okay? Sometimes the problem that you're trying to do has already been done. Okay? Let's say you want to identify cat from dog. Okay? Chances are the whole world has been trying to identify cat from dog. Yeah? If your problem is to identify llamas versus I don't know, some kind of strange animal, right? This is a weird animal, some kind of a more obscure kind of animal. Then that problem probably has to be solved. Yeah. So imagine this. Somebody already know that based on, think of example of the previous example, we have several lengths and width, and you can do 3 kind of items, right? So this problem has been done to death. You can imagine that there are other problems that are done to death, like data feature suite. By the way, I remember you have that. So let's imagine that this problem has been done to death. This problem has been done to death. Okay? This is 28 by 28 and written recognition. Right? This problem has been done to death. What do I mean by be done to death? It means somebody has already specified the neural network. Right? Now look at the board, guys. Yeah? Because this problem has been solved, somebody has specified the neural network architecture, but has also trained it. So I'm going to say something like train. So it has all the weight. It doesn't just have the coefficient, right? It has actual value of the coefficient. Yeah? So this problem is done. You have 3 situations. Okay? You have 3 situations. Situation 1. Your problem is exactly this. Your problem is exactly this. Yeah? But you want to apply it to different things to maybe your other handwriting, somebody else. Yeah? But you're going to be using 28 by 28 matrix as well, right? So why not just use the one that's already done? This one has the neural network architecture with the weight frame. Yeah, with the weight frame. So treat this as a complete push button. Yeah, just download this. In the old days, you can download executable. Yeah, like a digital file that you can't read. It's just literally an executable. Okay? So think of it as a dynamic link library. It's done. You can't do anything with it. You can only input something and get something solved. So if I input something like this, it's going to give me a prediction. Hopefully, it's going to be a good prediction. So your problem is exactly what has been done. Don't do anything new. Smart people with more expensive computers have done it. Download that. Two, your problem is kind of like this. It's kind of like this, but not quite. So for example, you have this kind of architecture, okay, 28 by 28 to 3. But in addition to 0, 1, 2, 3, 4, 5, 8, 9, you want to characterize, you want this character as well. You want to use maybe a highlighter, right? But you know that of this kind of complexity, what you would like to do is exactly what's been done. In which case, you copy this. But you don't copy the data. And you train the data. Okay? Architecture, and you retrain it. Finally, if your problem is completely different, you can just be inspired by the approach they do, see what they do. But you have to build your own neural network, special, and then retrain. Okay? This one you build from scratch. Okay, this is my figure. This one you build from scratch. This one you use their architecture but retrain. This one you use their architecture as is. Now, in between here, there's another layer called transfer learning. This is where, if you have the neural network that's trained, and this is input, and this is output, you know that your problem is similar, but not quite the same, but so similar. Chances are the first 3 or 4 layers do not have to be retrained. So you retrain just the latter layer. And I'll tell you why it makes sense when we go into other neural networks. Okay. So once again, what are your options? Now you have actually 4 options. Build your own neural network. That's the hardest one. Copy the architecture, retrain. Copy the architecture, copy part of the weight, and retrain the rest. That's like a version 2.5. And version 3 is the easiest one. Say use the trade model. Okay, so these are real life. Now, in the old days, when I was a student, for example, you don't have it. There's no such thing as a free trade model. Okay, everybody starts from scratch. Now, let's see how that works in action. So this one, the neural architecture, you can use pre-configured. So this is what I'm talking about here. Pre-configured from a model repository. Now, the digit recognition is one of those things. Okay? You take the pixel screen 28 by 28, give you a number. It has already been done. So you can do that. You can do this. Do this. Take the architecture and retrain. Yeah. So in this case, this is what I'm going to do. Okay, let's make it bigger. Okay. Now, once again, this data we saw earlier in the beginning of the class, I just downloaded it, right? And what does it look like? Let's see, random sample from the train, say, okay, and say about 10 of them. Okay, so that's my training data, right? It's a character 2, right? Okay, that's the data set. Now, let's say I want to copy, okay? I don't want to start from scratch. If I were to start from scratch, I would have to use this function, okay? Now, remember, you can do this, right? What we did before is something like classify and then neural network. This time we're doing something very difficult, so you have to build the neural network yourself. Now, I can build my neural network by doing my neural network equal to net chain. Okay, now net chain, let me press F1, see where it takes us. Okay, net chain does this. It tells you how to build the layer. Basically, it tells you the layer. Yeah? Net chain is building the building, but they call it chain rather than building. Yeah? So first layer, second layer, third layer, how many. Okay? That would be like building from scratch. Okay? We're not going to do that. We're not going to do that. We're going to take the shortcut. We're going to say, I'm going to copy my architecture. My neural network is going to be a net model called LeNet. LeNet is the name of the architecture. Okay? So this is kind of like a report story. It's like a library. Yeah? So it's like, you know, when you build houses, sometimes they say you don't have to design a house, you can do the pre-built plan, right? They tell you that, right? Three-story house has a perfect design. It's easy to design. Well, it's a bit like that. So this has the perfect architecture. They have done a lot of work and they say this is a very good one. You say, okay, this is what we do. So I say, my neural network is going to be a net model called LeNet. Immediately you get this object. Now let's expand it a little bit. It says the input is a 1 by 28 by 28. You see that? Right? Basically, it's saying 1 plus 1 color, that's 3 colors, and the screen is 28 by 28 wide. Okay? So the input is a screen, a pixel layer screen, right? Second, it's called convolutional layer. Now, that's a layer of neuron. Okay? But it's a very funny one. It's not the one you see. So don't worry about it. But that's important. The other one is called a wrap. A wrap is basically the very unit. Cooling layer is another type. So you can see there are many types. One is the 5 yeah, it's a layer of operation. But this, you don't have to design because this has already been designed. So this is like a template of a building. Okay? So if you do this, okay? If you do this, you don't have to come up with your own architecture. Okay? So if this were a building, you would say this building has 11 stories. The first story consists of 28 by 28 rooms. That's input. The second story has 28, 24 by 24 by 20 rooms of the type convolution. The third story is 20 by 24 by 24 rooms of the type random. Okay? The fourth is a story of cooling layer and but it's actually a vector. It's not a range of that. It's actually a row of 500 neurons. Okay? So the ninth layer is 500 of neurons. Of what type? RAM. What's RAM? RAM is the gray loop that we saw in the picture. And the media layer, softmax layer. So again, this is the architecture. Now, if you're building this from scratch, you have to use concepts like HA and XA. The first one, computational layer, RAM cooling layer of inside. But in this case, you can copy the previous architecture as a template. Now, the way Mathematica show this is to show it as a gray object and the word uninitialized. Okay? So by saying that my neural network is a net model of the net type, it gives you this architecture that's uninitialized, meaning it has no value. It doesn't have the weight. Okay? So it's like a neuron that has no density. Yeah? Because it has to be trained, right? So it has no weight. Yeah? Now, so it's just a blank neural network. It's like F is equal to AX plus B, but you haven't specified what A is, you haven't specified what B is, you just leave it blank. Okay? It's a placeholder. Now, I'm going to say, I'm going to train. Okay? My neural network is equal to net train the net, my neural network with respect to the data train. Now, because this is going to take a while, I'm going to add a target device GPU. Yeah? So I run that. Okay? So I run that. So originally I have my NN, which is a blank thing. Now it's training. Now it's training. Okay? Using, see that? You guys see this? Adam, right? Remember I told you? Not only do you have to specify the architecture, you have to specify the algorithm. But if you don't specify the algorithm, and I just said in this class, you don't have to specify the algorithm, because that's fairly advanced stuff. Mathematica will choose for you. And if you choose, normally we choose Adam or SD. In this case, we choose Adam optimizer. Yeah. So that comes sort of like a by default. Yeah. Because now Adam optimizer, I think, maybe the last year. So when I was doing that Adam optimizer, so it's relatively, well, it's not relatively new, but it's in the last 20 years, I think. Yeah, so it's training, it's training, it's training. Now this is real time, so it's it takes a while. It actually gives you 23 minutes. Now this is real problem. So it's going to last for 23 minutes or so. But I have already run it this morning. Yeah, so the error rate is going to go down, right? The error rate is going to go down. Keep going. But I'm going to stop because okay. Right. Basically, I ran earlier and I have this. Yeah, it's already trained. Now, once it's trained, it gives you the color to show that the value is already there. The same architecture, but now it has the value. Right, that's the value. So you can train that. And once you've trained it, you can try using it. So if I apply to this case, I get that. So is it accurate? It's perfectly accurate, guys. Right? I didn't solve it really, right? So 9 you got right, 1 you got right, 6 you got right, 2 you didn't get right. So obviously, it's not perfect. Okay? Now, when I did, this was based on earlier run when I finished. Okay? This is the confusion table. Remember, confusion table is for classification problem that works in multi-class, right? So in this case, you have 10 different values, 0, 1 to 9, right? And that's a confusion table. So that's pretty good. it run through software. Okay, you have to let it run through. So this is copy the architecture what we create on your data. Now, again, if your problem happens to be exactly the same problem, then you can use this as a calculator. So this is how you do it as well. A pre-trained neural network, you just download it. It's called limit train on this data. So there's like a catalog in a web page for Mathematica of the model that has been pre-trained. In this case, you don't have to train for 20 minutes yourself because it's already been trained. Now, if I click this, it would have exact same architecture as before, except it comes already with colors, meaning it already has a value, right? And so you can use it. Yeah, and it has, again, very good accuracy. So let me go back to this again. Today, we want to know the pipeline. Yeah, I made the not assumption. I made the conclusion that most of your projects have to do with what? With the exception of the ARIMA person, which I don't think is going to be viable very well. It's going to be machine learning based. Not only is it machine learning based, it's going to be mostly supervised learning. Supervised learning, regression or classification, but I chose to focus on classification because I think most of you guys are doing that. The classification can be binary classification or multiple class. Most of you are dealing with multiple class, except you. Well, I don't know if you're multiple class. Yeah? Maybe something like A beats B, that's 1. B beats A, that's 2. B and A are even, that's 3. You see what I mean? Let's draw. So you could be binary or multiple class, something like that. Yeah? But again, between classification and regression, most of the time I'm focusing on classification. So when we do classification, we have to do this pipeline. This pipeline, is you have to get the data, train, and that's a lot of stuff. For your problem, it's a lot of things. 2, we have to get the reprocessing. To get the data into basically a series of pair. X, Y, X, Y, X, Y, X, Y. Because that's exactly what supervised learning does. It gives you a pair of bunch of X, Y, and you have to learn to read Y and X. So that's how you get the data in format. Then you have to do this validation, which I'm going to talk about why you need that. But certainly you know about testing out sample, right? Principle, train of this data set, test about so in this case, I'm doing some kind of 80-20 split. Right? Once I do that, then I build the machine learning entity. Run it, experiment, test, get results, draw conclusion. Then the next slide is to focus on this. But it's not just building machine learning engine, it's building a neural learning engine. Yeah? So it's more complicated. Now, when you go to Mathematica or scikit-learn in Python, if you build, say, decision tree, okay? The set is fairly obvious. It's specified to be neural, giving you some parameter like an act depth or something like that. It's not very involved. You don't have to do a lot of design. There isn't a whole bunch of design parameters you can do. Okay? So you say something like, give me a decision tree with max depth of 5. Or random forest with 5,000 trees, or something like that. Yeah. But with neural network, you have to do a lot of specification. You have to specify the architecture. From input to output, there are many layers. So how many layers? And each layer, how many neurons? And what types are they? So this is what you have to specify. Once you specify, then you can train it. But to train it, you have to choose the algorithm for training. Then you have algorithms that take big step downhill, then smaller step, or sometimes take up to step, or take even number of steps. or depending on how you did. If you were improving a lot, take a bigger step. If not, then you take a bigger step so you can try something else. All kind of variation. At the end of the day, there are two varieties that comes out on top. SGD, which is a little bit older, and ADA, which is a little bit newer. For this class, we don't have to specify the learning algorithm. Leave it to the Mathematica or Python scientific. Okay, that's useful. But once you chose the architecture, you have to train. But when you choose the architecture, you can do this. And this is this thing. I want you to have this, right? If you're once again, let me say, repeat what I said earlier. Certain problems are done to death, like digit recognition, MNIST. That problem consists of a screen of 28 by 28 pixels, handwritten digits, and you have to make it recognition. If your project involves reading handwritten numbers, okay, Arabic numbers, not Roman, not Thai, Arabic numbers, handwritten on a square piece of real estate that can be pixelated into 28 by 28, you can literally use the neural network that has been trained using very expensive computer and download it, like what we did. So the net model with the name net trained on MS. Use that. If you have this problem, okay, but you want to add a little feature to it, so you don't have to recognize 0 to 9, but maybe you want to train a little bit more so that it recognizes special character like alpha, or special character like explanation mark or point, something like that. What you can do is take the pre-train and then retrain some of them. Or, in the case that I show you, retrain the whole thing. Yeah? And worst comes to worst, build it from scratch. Okay? Now, in your problem, you have this thing called object recognition from Google that recognizes objects in picture of fairly arbitrary dimension, I think. Yeah? So what happened is the algorithm is going to do is going to increase it. Okay? So maybe it has a default screen of 256 wide to 512 tall by 3 colors. Okay? So if your image resolution is different, there'll be some kind of pre-processing that squeeze into that dimension automatically, I think. And or whatever, or maybe it cuts a little block, or I don't know what it is. But Google definitely has object recognition. Google does not have object picture caption. Not yet. Not yet. So never mind. Just stick with this. Yeah, stick with recognition. So by using this, what version are you doing? You building from scratch? No. Are you retraining? No. Are you taking part and retraining stuff? No. You take the whole thing. It's okay. It's okay. Because Google has done a lot, you know, they have bigger computers than you do, okay? Than all of us do. So, if the pre-trained model can recognize cat, dog, cup, paper, woman, man, hat, shirt, shoes, okay? Then you don't have to do anything else. Just copy that. Use that. But once you've got that, that becomes an input to your other part. Now this is where you probably need to do it. Right? Because you have to map from something like a picture of a woman with 2 cats gets smile. A woman and a dog and a tiger gets shocked, something like that. Okay? So that thing certainly hasn't been solved before, right? Nobody has done it. There's no proven architecture for doing it. So you have to start from scratch. So you're going to build here. But the first step, so it's neural network feeding neural network. Yeah. with your thing, chances are you have to do this. Right? Because nobody has really built this kind of cobweb battle between football players. I don't think. Okay? So you have to think from scratch. But from scratch means what? You have to say something like, my neural network is equal to net chain of 5 layers. Try something. Okay? Now, this is all experimental. This is all experimental. But basically, there are some heuristic. For example, they say something like, well, if your vector input vector is size n, if you have the second layer to be in size no less than n divided by 2. Something like that. These are all heuristic. Okay? It's like saying if you need to put in a lot of people, if you want to fit a lot of people, should you have a tall building and very narrow or wide building but not very tall? It's not clear. It's not clear. Okay? It's not like this case. Okay? This case with Lynette, this guy already built and trained it. Okay? So you can literally download it. Okay? That's fine. That's not a problem. Yeah. So learning or transfer learning. That's great. In the future, by the way, guys, I'll tell you this. In the future, most of the applications will be done by transfer learning. It will be great because, you know, a lot of things like visual recognition, object recognition, it takes a lot of computer time. And if the Google has built the infrastructure for creating object recognition, then it's going to take that. That's basically how it's going to work. So this is going to, now, if you notice here, there are things like convolutional layer and so forth. We haven't talked about that. We haven't talked about, so you don't know that yet. So you just know basic. You just know basic items. Neural network comes with layers. The first layer fully connects to the second layer fully connects to the third. There are different types of neurons, but you don't have different types to the same layer, right? And between the layers, they don't send signals to each other. They kind of like together. They send signal from below, you see signal from below, send it to over. Yeah? Now, is that a limitation? No, not really. Not really. Yeah. Because there's this thing called universal approximation theorem. The universal approximation simply say, this is the last one. If you have that logistic sigmoid function type, if you have enough of them, you can represent any continuous function. It's a little bit like Fourier analysis. I don't know if you know Fourier analysis. You know what the sine wave is, right? You know what a sine wave is? Sine wave like this, right? Now, you put two sine waves together, they add. If I want to draw a picture of this mountain, okay? Universal approximation in that case, Fourier theorem says, if I have enough sine waves, I can add certain combinations, some big waves, some small waves, some big one on a smaller amplitude, shift a little bit, or change the frequency. If I add enough of them, I can draw any picture. Same thing. If I have enough neurons, I can make any mathematical function. Any in the world. Continuous function. Okay, why? Okay? So that's why we believe that, yeah, eventually we'll be able to build something. And that's something you cannot say of linear regression. See? Notice the two statements are very different, right? With things like logistic regression, we say, assuming your problem can be separated with a straight line, I can separate it. Neural network assumptions say, assuming you have computer to add enough neuron, I can fit any function. Yeah. Now, the theorem actually say infinite theoretically infinite, but you know, in practice, it will be hundreds and thousands, and that's what we have. All the visual recognition, all the Google, your iPhone, iPad, these are based on hundreds of thousands of neurons. Okay, maybe not hundreds of thousands, maybe 50,000, but a lot, certainly a lot. Okay, not infinite. Okay, so that's that. I think this should give you enough flavor. Now, I sent you guys the student pricing page for Mathematica. I think you should look into that further. You can just follow some project will be able to build in. Now, if your built-in is Google, then it probably makes more sense to use Python based, at least for the first part, because then you can link. Now, Mathematica can call Python, but it's very clumsy. Just go ahead and work in Python. Okay? Use Python Google library for object recognition. Once you get object recognition, then it's up to you. Okay? Once you harvest, once you do the pre-processing, you have the final X, Y, I-O, and there you can do anything. You use Python or Mathematica. Okay? The football, I would imagine, you can start with purely from Mathematica and get away with that's because you know Python is quicker computationally, but it's a lot more verbose, lots of lines. It's not high level, okay? But it certainly is quick because at the back it's a lot of times the C. Yeah. But I don't think you have a big data set. Yeah, they're not millions of football players. At most you have what, 2,000 in FIFA database? How many football players do you have? I would say less than 50,000 for sure, which is easy. On football, how many football players do you have in the FIFA database? More than 50,000? Okay, so how many? 50,000 players? Yeah, maybe 20,000 football players, which is nothing. So performance-wise, it's not an issue. So you can do that. Okay. So with that, I think it's good for today. On Monday, remember, you guys have assignments, right? We'll come back. I want you guys to start showing me like the coding part, the thing. Now you should be starting to do that. Okay. I might go back to lecture mode and talk about the CNN and LSTM. I think that's important. Or I might do that on the week after and see what happens. Okay, Kap. I think it's time for today. Thank you.